I'm convinced that the subject of the age of the earth is one of the most critical issues in the creation-evolution controversy. I'm a little disturbed with some of my brethren who say it doesn't make any difference. I think that's rather naive. I think we can show both from Scripture and from science that the best and most reasonable explanation is that the earth is young, in spite of the propaganda that we hear continually from the media. I believe science indicates that the earth is not old. But of course there are a great many scientists who believe that the earth is billions of years old, certainly not all scientists by any means, and there are a significant number who believe the scientific evidence is against this conclusion. But to get an idea of the role that this issue plays in the minds of the naturalist, notice the statement by Lawrence Badash, professor of history of science, University of California, Santa Barbara. And he refers to the general conclusion of many, 4.5 billion years ago. The primal earth emerged from a spinning turbulent cloud of gas, dust, planetoids that surrounded the new star. On these figures for the age of the earth rest all of geology and evolution. This is the foundation. Well, I think it's a pretty shaky foundation, and perhaps before we're finished this evening you can see why I believe that. But it's absolutely critical, obviously, to the evolutionists that the earth be billions of years old. If it isn't, then we can all go home. There's no time for evolution. But it's more than just necessary for evolution. It is necessary to solve all of his problems, and this is basically the way he looks at time. It's the solution to any and every problem that comes up. Consider the statement by George Wall, who is a Nobel laureate from Harvard. He's talking about the origin of life, and as he sees the complexity that we've learned about, it just boggles his mind and says, we can't imagine how this could happen naturally. And that's a necessary conclusion, and one that many naturalists will agree with. He says one only has to contemplate the magnitude of this task, that is, getting the cell to start all by itself, to concede that the spontaneous generation of a living organism is impossible. Well, how does he solve that problem? Yet, here we are as a result, I believe, of spontaneous generation. Now, it's impossible, but he believes it because he's got time. However improbable we regard this event or any of the steps which it involves, given enough time, it will almost certainly happen at least once. Now, as we looked last night at the implications of time, things tend to go uphill or downhill. Time doesn't help in trying to get things organized and more complex. Time does the opposite in our experience. But the faith of the evolutionist says it'll solve all the problems. Time is, in fact, the hero of the plot. Given so much time, the impossible becomes possible. The possible probable, the probable virtually certain. One has only to wait, and time itself performs the miracles. So here's the Holy Spirit of the evolutionist. You just wave the magic wand and all the problems disappear because of time, in spite of what we learned last night about time causing things to go downhill. We're reminded of the fairy tale of the princess that kisses the frog and then turns into a prince, and of course that's a fairy tale, we understand, unless you add the magic kiss of time, and then it's science. Over billions of years, this is exactly what happens. And that's what our universities are spending billions of dollars to teach, that yes, the frog turns into the prince. The only difference between it and the fairy tale is time. And I don't think time has that property, that power, that miracle working capability. I think one of the best ways to approach issues in science is to ask why questions, and I think that's especially appropriate here. People are just absolutely inundated with affirmation after affirmation, like a mantra, that the earth's billions of years old. Well, why do you believe that? I think is a good question. And of course, it is a matter of faith. Nobody was there at the beginning. They believe that the earth's old, and my question is why? Well, usually the first response that we get to that question involves radiometric dating, because they've dated the rock. The rock is 1 million, it's 1 billion or 2 billion, 4 billion years old. They don't date them that old, but 3 billion sometimes. And obviously the earth has to be at least that old. And of course we all understand exactly how this radiometric system works, so that we can evaluate the validity. No, we don't have a clue how it works, do we? And most of the scientists don't, believe it or not. We just have faith because they tell us it works. We announced the subject of radioactive dating not too long ago for some teenagers, and I think they got the wrong impression. Generally, radioactive material is material that emits particles from the nucleus of the atom. It's not stable, and through the loss of alpha and beta particles decays into different elements and finally winds up as a stable element. And this decay process is supposed to allow us to tell time, something like an hourglass. You begin with an hour's worth of material at the top. It decays down in an hour's time to what's at the bottom. And so this is the way you can tell time. Now, as you look at uranium, it loses some of its 238 particles, becoming other minerals, coming finally to be lead, which is stable. There's natural lead and radiogenic lead, but this is what's produced as a result of the decay process, and then you use the equation that you see here to reach the conclusion about the number of years. What could go wrong with this kind of a process? Well, let's look at the hourglass and just say how much time has transpired here, ignoring the uranium and lead for a second. If we're looking at a regular hourglass, how much time? Well, we can look at that and we can say maybe 15 minutes, maybe 20 minutes. And if we could count the grains of sand, we could come up with a very accurate conclusion about how much time had transpired, assuming that the rate is constant. But what would go wrong? What could possibly be wrong with that conclusion? Suppose just before you looked at the hourglass, somebody raised the top and dumped in a lot of extra sand, and virtually all of the hour's worth of sand had already run to the bottom. Now it looks like it hasn't. And it's been going for 58 minutes, but now it looks like that's not the case. Or suppose someone lowered the lid and let out most of what had already run down. Or suppose it were basically like this, laying on its side, and it'd been going 2 seconds when somebody set it up and now say, look at it. You have to know the beginning conditions, and you have to know that it's a closed system, that nothing leaked in or leaked out, or you're not really telling time. And these are the basic problems by analogy. Now, it's a rather crude analogy, but gives us an idea of what we're talking about. Notice Henry Fall's statement, one of the leading authorities in this field. He says 2 important assumptions are implicit in this equation, the one we looked at just a moment ago. First, that we're dealing with a closed system. Nothing leaked in, nothing leaked out. Second, that no atoms of the daughter, that's what's produced at the bottom, were present in the system when it formed. And non-radiogenic lead occurs throughout nature. These assumptions furnish the most serious limitations on the accumulation clock. Now, this is not the creationist, this is the evolutionist saying this is a serious problem. He continues saying rigorously closed systems probably do not exist in nature. But surprisingly, many rocks and minerals satisfy the requirements well enough to be useful for nuclear age determination. The problem is one of judicious geologic selection. And so this is not an objective process. You date the rock and you get an age. You know most rocks really don't fit the purpose, and You just judiciously select the one that's going to work for you. J.D. McDougall is writing in Scientific American saying that this process involves rocks where you have minerals leaking in constantly. Groundwater percolation can leach away the proportion of uranium present in the rock crystals. And the mobility of the uranium is such that as one part of the rock is being impoverished, another part can become abnormally enriched at relatively low temperatures. And when this is going on, you're adding sand to the hourglass, or you're taking away sand from the hourglass, and what does that do to the time-telling mechanism? It's just really messing it up, isn't it? You can't tell time that way. We see things that become fossilized, that become petrified. How does this happen? Well, water percolates down through the rocks and it leaches out some material, it replaces it with other material, and this is not that unusual. And that's going on in rocks all the time, especially if you're looking at billions or millions or thousands of years. Miger of East Carolina University really gets down to how it works, writing in Contributions to Geology, when he says, in general, dates in the correct ballpark are assumed to be correct and are published, if it comes out, quote, right. And by the way, if you send in a sample to a lab, they're not going to date it unless you tell them where it came from, how old it's supposed to be. They don't take the test unless you give them the answer. And that's not the way I used to take tests. All you got to do is log on the websites, look at the form where you submit the samples, and see this is what you have to tell them. And I'll guarantee you they don't do it. There may be one or two, but they're not the reputable labs. Continuing, he says, those in disagreement, if they're in agreement, they're published. If they're in disagreement with the other data, they're seldom published, nor are the discrepancies fully explained. They don't even try, they just chuck it. Now that sounds rather cynical, and surely scientific people can't do it that way. Well, let's allow the evolutionist himself to describe exactly what's happened. One of the more famous examples of dating involves the 1470 skull by Richard Leakey, and Roger Lewin is editor of Research News and Science, one of, if not the most prestigious science journal in the United States. He is a good friend of Richard Leakey's. They've written a couple of books together. And he's describing how the dating of this took place. And really there's a couple of chapters in his book, Bones of Contention, which is a pretty interesting book. You know, he, of course, believes in the billions of years and is a devout evolutionist. But historically, you've got a pretty good record of what happened in the search for fossil man. The calculated age was quickly refined to be 2.61 plus or minus 0.26 million years. Okay, 1470 skull. 2.61 plus or minus 0.26 million years, which to the anthropologist unfamiliar with the procedures of radiometric dating has a ring of comforting precision about it. Well, even the anthropologists, I mean, you don't feel bad, they don't really understand how it works either. And this sounds very comforting. But let's look at the rest of the story. There were 41 separate age determinations, which varied between 223 million and less than 1 million. Now that's a huge range. 41 different tests, and it's all over the place. And they never, after the first determination, never again obtained 2.61 from their experience. They got it 1 out of 41. And chucked the 40 and kept the 1. Now, that's not my description. This is Leakey's best friend, editor of Research News and Science. This is the way it works. You just keep chucking until you get what you want. Now, how scientific is that? This is a game that's played to verify what you already believe. If it doesn't, you chuck it and you keep playing. Let me give you some more illustrations. This is a cross-section of the Grand Canyon, and we've done some research here. I say we, myself, with several others, mainly others in this area, but we work together. As we look at this cross-section of the canyon, we can determine that some rocks ought to be older. Certainly, if the evolutionary picture is correct, the ones down at the bottom ought to be older than the ones up at the top, right? The Uinkaret basalt has come out of what appear to be modern volcanoes. Some have suggested the American Indians saw these eruptions take place. They flowed over the edge of the canyon down into and damming up some of the lowest parts of the canyon. This would be the youngest rock there. Interestingly, the same type of rock is found down in the intergorge, underneath the sedimentary layers, down in the igneous rock in the inner part of the gorge, but it's the same kind of rock, cardenous basalt. Which ought to be older? Well, it's obvious which should be older. Okay, let's send these rocks to the lab and see how this works out. Well, which method will we use? There are about 20 different radiometric methods, but some of them would be more appropriate for this type of rock. Here we use several different methods to date the Uinkaret basalt. 6 potassium-argon model ages were run, and the range was from 0.01 all the way to 17 million, which is a pretty good range in itself from this one lab. The rubidium-strontium came out 1270 to 1390. The lead-lead isochron, supposed to be the most accurate, came out better than 2.5 billion, which is a whole lot more than the 17 million, which was the oldest potassium-argon age. Now this is the same rock. Different methods on the same rock. Now you're told over and over again that we test and the same, the different ages come out and they are concordant and they verify one another, and this is the way we check and we know it's right because they all agree. If you chuck 40 and pick the one and then you're able to do that with the others, maybe you can come out with something that looked concordant, but this is the real experience that we had. With the cardenous basalts, let's see how that came out. Similar methods used, and again, that's all over the place, from 853 million to a billion. Huge range. Again, all from the same rock, just using different methods. But we compare the oldest rock from the Uinkaret Plateau that flowed over the edge and dammed up the lowest part of the canyon, and it's 2.5 billion, whereas the oldest age for the oldest rock is just barely a billion. It's less than half as old as what flowed over the top of the canyon. Now, how is it that you got the lower younger? It ought to be much. There sometimes when you can test and know, at least relatively speaking, what ought to be, and when you do, I'm sorry, it doesn't work unless you do a lot of checking, which is done as we have demonstrated from the evolutionist himself. We decided to do some work at Mount St Helens. This is a picture of the caldera. The center portion is of known age. This is from 1986. The eruption was 1980, but 6 years later is where most of this was extruded. We took 5 samples from the caldera, different parts of it, and sent it to the lab. Here's the rock, you date it. Tell me the age. Well, the answer came back looking like this, in millions of years. And the rock was actually 11 years old. And people will say, well, okay, it was not dating when the rock formed, but rock that was already mixed together as lava, and that's, of course, exactly right. The assumption of the potassium-argon dating, which was being used here, is that when it flows as lava, all of the argon escapes, and when it then congeals into rock, that's when the clock starts. And you're dating the time when it became hard as rock. Sorry, it doesn't all escape. There's still plenty of argon there. It doesn't work. and gives absolutely absurd results. This is not unusual. And if you're chucking 40 out of 41, then I think you get the picture. Radiocarbon dating is the one that we hear a good deal about. It's not nearly as significant for evolution because it covers a much shorter period of time and works somewhat differently. It covers a period of less than 100,000 years, probably more like 60 to 70,000, which I think is significant when we're talking about the age of the earth from the biblical perspective, but not the billions necessary for evolution. Robert Lee is commenting on, I think, rather objectively, the problems that have become obvious in recent years. He said, the troubles of the radiocarbon dating method are undeniably deep and serious. Despite 35 years of technological refinement and better understanding, the underlying assumptions have been strongly challenged. Now, this is not just something leaks in or leaks out. This is not just contamination. The underlying assumptions have been challenged. It forms in the upper atmosphere. The assumption is that there is the same amount relative to carbon-12 that there has been for thousands of years for the time that it's being tested. We have found that's not the case. That is, the carbon-14 is increasing. It's not staying the same. Libby, in his original work, said it would only take 30,000 years to reach this state of equilibrium, and it's not there, which is interesting. But he continues saying, it should be no surprise then that fully half of the dates are rejected. That's, I think, overstating his case. He is, of course, a believer in this and uses it. I have a friend who runs the carbon dating lab at Ball State University. He's a brother. We differ on the age of the earth. And we were discussing this, I think, in a brotherly way. And I was visiting him there at the lab, and he was dating a peat bog with the carbon-14 lab that he had, and he had chucked the first 19. He was on the 20th date. He knew it was 20,000 years old. Most of them had come out 4,000 and 5,000. Therefore, it proved that it was contaminated with recent material, so he's going to get a good one yet. But he's chucked everything he's gotten so far, 19 out of 19. And so when he says half the dates are rejected, I think he's understating the situation. He continues to say there are gross discrepancies, the chronology is uneven and relative, and the accepted dates are actually selected dates. Now, I submit to you this is not science. This is a game that's being played in order to make people look like they know what they're doing, to verify prior conclusions. Even W.D. Stanfield, who is a vicious anti-creationist, writing in his book Science of Evolution, it is obvious, and this is after we had presented some of this material, that the radiometric technique may not be the absolute dating methods they're claimed to be. And I think that's for obvious reasons. I think one of the best ways to approach this is to look at what might be called the proof of the pudding type arguments. Let's look at situations where we should be able to tell, at least relatively. The Grand Canyon would fit into that category. This is from the Glen Rose limestone, not too far from here. This is supposed to be 110 million, Middle Cretaceous. Well, a friend of mine, an associate, sent this to the UCLA carbon dating lab without being completely straightforward about where it came from. It came back dated at 890 years old from 110 million year old limestone. About 50 yards away, there was a carbonized stick in the same layer, and so he sent some of this to the same lab. It came back dated 12,800, which is considerably more than 800 years old, but all considerably less than the 110 million. Now, if you kept sending, you might get one that they would accept, because the response would be, well, you're crazy. You don't send material for radiocarbon dating from 110 million year old limestone. It's all gone within 50, 60,000 years. Now, it should be. But guess what? It's not. We have dated over 100 dinosaur bones now with radiocarbon dating. This is the ilium bone there from Glen Rose, supposed to be 110 million years old. It came back dated 19,000. It's a long ways from 110 million. And in 65 million years, since the dinosaur is supposed to have been extinct, all of the carbon-14 will be gone, like in 50 or 60,000 years. And so you're crazy for even trying to date dinosaur bones. If you think it's 110 million years, yes. But I don't. And we've dated over 100. Every single one of them, 100 out of 100, had significant radiocarbon in it. Therefore, I think they're playing games, and it's not 110 million years old. There are some obvious assumptions that you're not always told about. They dated it, this is how old it is. First, you have to know you're dealing with a closed system, and there virtually is no such thing. Things leak in and leak out. You have to know the beginning conditions. It's simply a matter of guessing how much lead is radiogenic and how much lead is produced naturally or is there naturally. There are some reasons for some of the assumptions, but it's a guess. And then you have to assume that the rate is constant, and there are some very serious challenges to that, and that may be even more productive than the ones we've looked at this evening. But when you see these assumptions that you don't know and can't know, and then you see that known relationships contradict, like with Mount St. Helens and the Grand Canyon, then you see why Stanfield says that there may not be good radiological clocks. He goes on to explain his statements, and age estimates on a given geological stratum by different radiometric methods are often quite different, sometimes by hundreds of millions of years, as we've shown. And so he says there is no absolutely reliable long-term radiological clock. Now, he still uses them and believes the Earth's billions of years old, but I think he's right, and I think that for, good reasons. Now, why do you think the Earth's old? Radiometric dating is really not a very good reason when you learn the facts. The second answer that we get typically involves geologic phenomenon. Everybody knows it takes a long time to fossilize things and to petrify things and to have all of these layers that we see in the Grand Canyon. Takes millions and millions of years, and look at all the sedimentary rock, and it takes millions of years to form that. And we look in the textbooks of stratigraphy, tell us about the sedimentation rates. This is by Schuster. It's still in all the textbooks. And this is the standard conclusion about how long it takes to form 1 foot of Paleozoic limestone, 2,700 years. That's the majority of it. Different rates for different portions, we're told, according to Schuster. Now, some would have it much, much older. This is actually a very conservative estimate. In '96, this book was published making the statement a rate of 1 centimeter per 1,000 years is typical. Now, that's over 30,000 years per foot. Most would say that's rather extreme, though these people from Yale and Dartmouth are very representative authorities. 30,000 years, or even 3,000 years a foot, is how this sediment accumulates and how the rocks form. It kind of reminds me of the Family Circus cartoon. The little boy says, how big does a stone have to grow before it becomes a rock? It's growing real slow. Do rocks grow? Have you seen? Or do they deteriorate? If they grew even at the slow rate, you just wait long enough and you got a rock house, you could have an extra bedroom and a new den. Rocks don't do that. They deteriorate, and we should understand that. But that's not the propaganda that's put out. Notice the picture here of the beautiful fossil spider, wolf spider, the fluorescent fossil beds. And there's a sign there at this national monument that says, remember, 2 inches equals 1 million years. Now that's slower than Officer and Page, but still on the order of what you typically hear. This is what we're paying for with our tax dollars. Now, just think about this for a minute. This is the width of a human hair. How long is it going to take to cover that hair at 2 inches per million years? At Schuster's rate, that's the one that's faster than the others. 2,500 years would be required to cover one hair. And what's going to happen to the spider as it's being covered at that rate? Is it still going to be there? Is it going to sit there and hold still for 2,500 years while the rock grows around it? That's the kind of thing you see in the textbooks. That doesn't even make good nonsense. If you just think, I mean, it doesn't hurt. Just think about it. There's no way that that's going to happen. Dunbar and Rogers, in their Principles of Stratigraphy, talked about this problem as a dilemma. When you look at the rocks and you see the fossils and try to imagine how this could happen slowly, you've got a problem. He says to some thoughtful stratigraphers, this amazing discovery, billions of years, presented a dilemma. For if the known stratified rocks have been accumulating throughout this vast span of time, the average rate of deposition must have been extremely slow. 3,000 years to form a foot, the faster rate instead of 30,000. Yet there is very good evidence that individual beds accumulated rapidly. Very good evidence. Now, where's the evidence, good or otherwise, that it happened slowly? No, the evidence is the opposite. What's he talking about? Well, we look at this shrimp, which is really not accurate. This is not a shrimp. This is a rock. And my question is, how long did it take that rock to form? Now just think about that. You know the shrimp is going to lay out there on the beach after it dies for years, days. How long? You ladies know you can put the shrimp in the refrigerator and it'll just stay there for years and years and years. How long is this shrimp going to look like this before it's solidified into rock? Well, if that rock is not formed within days, this picture you can't see. I mean, it just doesn't happen. These are some fish from Ennis County, not too far from where I live. Big, fat, juicy, plump fish that you lay out there in your backyard and it'll stay that way for years and years and years. How long are these fish going to stay this way? They became a rock while they're still looking like this. How long did it take that rock to form? We're looking here at a picture of a fish eating his supper. A heron and a perch, which are very similar to modern ones, supposed to be 135 million years old. The big one here is about 3 feet long. I enjoy eating with my brethren from time to time, and some of them we kid about being kind of slow in their eating processes. But thousands of years is kind of not. I mean, how long did it take this fish to become a rock? He got caught eating his supper. He got caught in the concrete, if you please, fast forming concrete. We're looking here at a fern, but this fern has not had time to wilt, and it became a rock. This one is bent over, as is the live fern that we see below it. Obviously, before it wilted, how long does it take a fern to wilt? You ladies know something about that. Just a few minutes sometimes. But this one looks beautiful, and it's a rock. Now, if we just think, we ought to know that this 30,000 years a foot, 2,500 years to cover a hair, propaganda in the textbooks and in our national monuments is just not even good hogwash. We're looking here at about a 43-foot fossil tree trunk. The bottom portion of it is protruding into a coal seam, and the top of it is protruding into a coal seam. And in between you have hundreds of layers of sandstone. The coal seam obviously took hundreds of thousands of years to form. I mean, we all have heard that. What's going to happen to the top of the tree while that's happening? Obviously, this is one event. This is not hundreds of thousands of years. What would it take to do something like this? Something like a flood, I think. Dunbar and Rogers again comment, 1,000 years more or less would have been required to bury a shell 5 inches in diameter. This is at the rapid Schuster rate. With very local exceptions, fossil shells show no evidence of such long exposure. Now, as he said, there's very good evidence that they formed rapidly. I want to know where the evidence is that it happened slowly. You look at the seashells. This is one from Dallas, a beautiful ammonite that's still iridescent. Some of the live shells that are iridescent you can lay out in the sunshine and it's gone in an afternoon. This is supposed to have been there for 35 million years. I think it was fossilized very quickly. Some of you will recognize the jellyfish. That little girl defining this for us the other night, well, she said it's just a bunch of snot. A pretty good description of it's not much, you know, it's not very stable. Lays out on the beach for how long after it dies? Long enough to be fossilized. Here are fossils of jellyfish, together with the ripple marks, which likewise don't last very long. A close-up shows even the mouth parts preserved of the jellyfish. Now you think, is it possible to do that slowly? This is an ichthyosaur that looks like a fish. It isn't. It's a reptile. It's about 28 feet long. Frozen in the limestone, Solenhofen limestone in Bavaria. Even some of the soft parts are beautifully preserved. We see the adipose tissue up here on the head, fatty tissue. And then we look closely at the interior and we see this is a Mrs. ichthyosaur. The embryo is seen. And a number of these obviously were caught in very catastrophic circumstances and buried, and it really upset the Mrs. ichthyosaurs because numbers of them are involved in premature birth in this one area. They got caught in a big storm and got buried by the sediment, and it really upset them, and here they are giving live birth. And I can sympathize with some of the ladies that think, well, this is going to take 100,000 years to get over. But it really doesn't. Nor did it with Mrs. ichthyosaur. There is no way to do that. So when you look at the rocks, the geologic phenomena, it says rapid everywhere you look. We talked about evidence for the young Earth. Well, also the evidence why they believe that it's old. Radiometric dating, well, that's not too good. The geologic phenomena is what I really like to talk about. And from that, I think we can see good evidence, as even many of the paleontologists today, perhaps most, would acknowledge. The individual rocks happened rapidly. Dunbar and Rogers, as we saw a moment ago, says there's very good evidence that the individual beds accumulated rapidly. And he's not saying that because it's fun to say for him, but because of the kind of evidence that we were looking at. But you ain't seen nothing yet. Let's look at willow. This is an amazingly preserved dinosaur, North Carolina State University, with heart intact. Now, we see some of these programs where they're trying to transplant the heart, and they get in the helicopter and they put the thing on dry ice and they run across the roof of the hospital and dash into. Because why? It deteriorates quickly. But this became a rock before the heart deteriorated. Here in the museum sign, what are the odds of finding a fossilized dinosaur heart? The seemingly impossible has occurred within the 66-million-year-old skeleton, which they have no doubt about, of course. Here we see the picture of the thorax, the chest, with the heart intact. And they've done CAT scans and all kinds of examination. This shows the clavicle, the collarbone, the neck bone here, but right here in the center is the heart. And there's the right ventricle and the left ventricle of the dinosaur heart. And in the center, the interventricular septum, all beautifully preserved. Now, how long did it take this? Now, this is not a heart. This is a rock. And how long did it take to form? At the rate of 2,500 years, it would cover a hair. I mean, this is idiocy. You just don't have words strong enough to describe the nonsense here. From National Geographic a few years ago, here's a mummified duck-billed dinosaur, 90% covered in soft tissue, stomach contents so well preserved, researchers can tell what he had for his last supper. But, of course, he was covered at the rate of 2,500 years to cover a hair, 30,000 years a foot. But it gets worse. We're looking here at dinosaur blood cells from a T-Rex. Blood cells, of course, last millions of years. Had to be 65 million. And this was what was written in Science Research News back in '93. Round, tiny, nucleated, they were threaded through the bone like red blood cells and blood vessels, but blood cells in a dinosaur should have disappeared eons ago. It was exactly like looking at a slice of modern bone. The bones are, after all, 65 million years old. How could blood cells survive that long? And, of course, the author is just asking the question, but there was a furor, and the lady that wrote this lost her job, got in serious trouble. But she decided to do more work, and she persevered and got her doctorate. She is now Dr. Mary Switzer at North Carolina State University, and has continued this investigation and has found some amazing things published just fairly recently. Now, her colleagues will say this is impossible, but she says here it is. This is the squishy, gushy, soft tissue from a T-Rex. Now, I was writing her about this particular specimen, and she acknowledged our current theories do not account for soft tissue and cellular preservation. Never in my wildest dreams would I have predicted what we found. It's certainly not anything like what you see in the textbooks or according to the theories. It was reported in Discover in April of '06, and she was interviewed. She said, I had one reviewer tell me that he didn't care what the data said. He knew that what I was finding wasn't possible. And it's not. If it's 65 million years old, he's absolutely right. I wrote back and said, well, what data would convince you? And he said, none. Very scientific. And he's telling the truth, believe me. The evidence doesn't matter. Since then, she's just found a wealth of material in the Tyrannosaurus rex bones, the gushy, stretchy, soft tissue, blood cells, blood vessels, and it is not possible for it to be 65 million years old. The conclusion is these dinosaur fossils cannot be old. It's impossible. And, of course, the evolutionist knows that. Now, let's think about that for a moment. I mean, it won't hurt. Let's try it. If the fossils in the layers are formed rapidly, and from the things we've looked at, the jellyfish, the little stretchy, gushy blood vessels. If the fossils in the layers are formed rapidly, wouldn't it necessarily follow that the layers that the fossils are in followed rapidly? I think you have to reach that conclusion. And so when we're looking at all of these layers, all of which have the kinds of fossils we're talking about in them, then we're talking about something that did not take millions of years. Well, then where is the time? And even the geologists today are saying, well, yes, we know the individual layers formed rapidly. Okay, if you know that, where's all this time? And they have an answer today. They say it's in between the layers. And I say, you mean where there is no evidence? And that kind of slows them down a little. But it's worse than that because there's evidence in between, as we'll see. But let's let them say this for us. Here's, at the time, President of the British Geological Association, in his book, New Catastrophism, President of the British Geological Association says, we cannot escape the conclusion that sedimentation was at times very rapid. You look at the trees, he referred specifically to the polystrate trees. But at other times, he says, there were long breaks in the sedimentation. Now, what's the evidence for the long breaks? Well, that's where there is none, but he's confident that it's there, admitting it looks uniform and continuous, but we know. I mean, after all, we know dinosaurs were 65 million years ago, and so there have to be breaks. It doesn't look like it, but we know there had to be. And when you look at the rocks, yes, it looks uniform and continuous. And you can tell when it's not. You have what we call bioturbidation. If a surface is exposed for any period of time, for less than a year, you've got clams burrowing, you've got worms burrowing, you've got plants sending down roots, and they just plow up the surface, and they don't leave these smooth, straight lines. They're eroded and they're plowed under or over or within. But what we're looking at here is straight and level and smooth, with the interfaces perfect in many instances. But he's sure it's there somewhere. He says the geological record is constantly lying to us. You don't listen to it. It pretends to tell us the whole truth when it's only telling us a very small part of it. Nowhere in the world is the record or even part of it complete. He imagines something much more than is there. It may seem paradoxical to me, but the gaps probably cover most of Earth history. And so he's basing his conclusions mostly on what's not there. I think you ought to base your conclusions on what is there. Is that better science? It was during the breaks that most of the events probably occurred. He has faith in that. It's not because of the evidence, but it's the lack that he depends on. It's the gaps that really matter. Now that just boggles my mind that a scientist could say it's not the evidence that matters, it's where there's not evidence. That's what matters. And that's where I'm going to tell my story, and that's where most of it took place. The individual rocks, yes, they happened rapidly. Well, we've got to get time in there somewhere. It's in the gaps. That's where most of it happened. Well, let's look at some of the gaps. Here's the Coconino Sandstone and the Hermit Shale down toward the base of the Grand Canyon. And here's the interface. Now, this is it looks uniform and continuous, but according to their dating of these rocks, there's at least 110 million years in between these two layers. That's what the geologic column says. Well, there was erosion for 110 million years, which left a straight, perfectly conforming line. Flat, smooth surface, not bioturbidated, not eroded. That takes a lot of faith, doesn't it? That's certainly not what it looks like. And when we look at the canyon, that's the way it looks from one end to the other. It looks smooth and straight at the contact lines, not like there was bioturbidation, not like there was erosion. it looks like one continuous deposition. A year-long series of catastrophes, I think, would do an excellent job of explaining this. Consider the contact lines. Where there is no evidence? Well, no, there is evidence at the contact lines. Here's one of them, and we're looking at little bird tracks. And the little bird walks along in the mud, and that's going to stay there for 110 million years before the next cover comes over it. Even if you did form it rapidly, and you've got the track in the rock, like in the concrete, then what's going to happen in the tens of years if this is exposed? You've got to have it covered quickly. The next one has to come quick. This is not merely a lack of evidence, but there is evidence at the interface. The most common feature in between the layers are the ripple marks. And it's been said that if you follow any bedding plane far enough, you'll find ripple marks. They're that common. Schrock, in his rock book, as we called it, Schrock's rock book, because they were one of the commonest, most widespread of original sedimentary features, ripple marks are preserved in conglomerates, sandstones, siltstones, clastic limestones, dolestones. There are no rocks that don't have ripple marks. Many examples have been described from rocks of all ages, I would say environments rather than ages, but all kinds of rocks all over the world have got ripple marks. This is from down at Glen Rose with the dinosaur tracks, which, by the way, are not going to stay there for millions of years. Any tracks are going to be eroded quickly, usually with the next rain, but ripple marks here are beautifully preserved. Now, the host layer that forms these ripple marks had to be formed rapidly in order to preserve them. These little ripple marks move from minute to minute as the water runs over the sediment at the bottom of the stream. But this is frozen in the rock. Then, once it's frozen in the rock, if it's not covered, it'll be eroded within tens of years if that surface is left exposed. And so the next layer had to be rapid to prevent erosion. And so the host rock has to be quick, and the one on top of it had to be quick, and the one on top has ripple marks on top of it, and so it had to be quick, and the one on top of it had to be quick to preserve it, and so on we go up the column. Virtually all layers have ripple marks at the bedding plane, which says virtually all of these layers have to be rapid, one after the other, to form and to preserve what's at the interface, where there is good evidence. It's not just a lack of evidence, which is bad enough. There is evidence, and it's very negative when you look at the interface. But let me show you something that's a real killer. Now, you've got to think a little bit. But this refutes, I think, conclusively, the picture that we're typically presented in the geologic column. Here's the Red Wall Mississippian, the most dramatic layer that you see when you go to the canyon. Mississippian is almost halfway up the geologic column. The lowest layer in the column is the Cambrian, and the Muav limestone here is Cambrian. So here's the lowest layer, Cambrian. You skip the Ordovician, the Silurian, the Devonian, and get up to the Mississippian. There's almost 200 million years that are missing between the Red Wall and the Muav. Now, how do you skip 200 million years? Well, if you've got deposition in one place, you've got to have erosion somewhere else, and so there was erosion here during that period, which left these straight level lines that you can trace for 300 miles up the canyon. But that's not the only challenge, just the fact that it's missing with a straight line in between. As you look above the Muav, you see this thin piece of red wall, but then above the red wall, you see more Muav. Now, you skip forward 200 million years, and then you come back 200 million years in order to get some more Muav, and then you go forward, and then you go backward, and then you go forward, and then you back and forth, skipping 200 million years, backwards and forwards 8 times. Ain't no way. It's interbedded And the fundamental rules of stratigraphy indicate if it's interbedded, it must be contemporaneous, even though the geologic column says it's 200 million years apart. It can't be. It is absolutely impossible. It looks continuous without the bioturbidation. It is continuous. It cannot possibly be millions. These two cannot possibly be 200 million years apart. They are interbedded. And so geology fails. When you study the rocks, you know this story is a tale that does not fit the facts. But how do you, can you really envision forming all of these layers quickly? Well, let's look at it happening. Mount St Helens is a demonstration of what happened. 1980, it blew its top, and the pyroclastic cloud went across the countryside at almost 200 miles an hour and laid down sediment here, forming Spirit Lake, the trees across the top. And then when Spirit Lake broke through the temporary dam, it eroded down through the newly laid sediment, leaving this huge canyon up to 600 feet thick, that is deep. Here's another picture, 600-foot cliff over here. And this is rock now. And this little trickle down at the bottom is what cut this big canyon. You think? I don't think so. It was a whole lot more water that eroded that canyon. And that reminds us of another story that's being told. But we look at the walls of this canyon, and you see these finely graduated, laminated layers that happened one afternoon at almost 200 miles an hour. We were told in class, you count these little layers, it's at least a year per layer. Probably more, but at least. And so you had the job of going out and counting the layers and seeing how many thousands of years were represented here. 600 feet of this happened in less than 3 months, most of it in one afternoon. And then with the erosion through that, you have a canyon that looks for all the world like the Grand Canyon. A 40th scale Grand Canyon, the same side slumping canyons, the same geomorphology. It reminds me of the cartoon that a friend of mine drew. This million-year-old canyon was formed by Mount St Helens in 1980. Yeah, that's the story. But it's also the demonstration of what I believe happened. And we can see that. Did you see it forming slowly? No. You saw it forming rapidly. Which is better science? We've all seen the speleotherms in the caves, the stalactites and the stalagmites, and heard the spiel. These are hundreds of thousands of years old. I was taught in my textbook there at Indiana University, it takes at least 100,000 years to form 1 cubic inch. And at that rate, it would take a long time to form these tall speleotherms. This one from North Alabama. The previous one from near Bedford, Indiana, which is not too far from where this picture was taken. This is the George Rogers Clark Memorial near Vincennes, Indiana, on the banks of the Wabash River, a clay bank here. And the limestone here was quarried from within just about 3 miles of where that slide before last was taken. Same limestone, water percolates down through the cracks in the rocks, and in the basement we have speleotherms, just like we do in the caves. The building, when these pictures were taken, was 40 years old. It's a very interesting story how these pictures were taken, because they would not allow anyone in, even the National Speleological Society. We had to threaten to cut their funding off through the legislature, which they then responded to. I think I could have had one of those columns when I finally showed up, but I did get in, and there were 5 of these columns, and they just didn't want people to know what was going on. In New Zealand, a friend of mine sent me this picture of the Zinc Mine. Notice the people over here in the lower right-hand corner. This was a 30-year-old tunnel with a concrete bunker there across the middle. Obviously takes hundreds of thousands of years. I have an associate who is referred to here in Arizona highways, Jerry Trout, and a good friend who works with Jerry Trout down in South Texas, Sonora Caverns. And here they report, while some believe beautiful icicle-looking stalactites take years to form, Jerry Trout, cave specialist with the Forest Service, says that through photo monitoring, he's watched a stalactite grow several inches in a matter of days. And his associate told me of being there when they set up the camera on time-lapse photography, and the thing grew past the lens and out of the frame in a month, and so they had to back up and do it quicker. It's just not so that it takes millions of years. Here's a scene from Carlsbad Cavern. Of course, there are a lot of bats flying around there, and one of them got trapped in a stalactite. Real slow bat. We're looking here at a boot. We're familiar with that here in Texas. This is from out in West Texas. Inside of it is a petrified cowboy leg with flesh, including bones, that are fossilized. Some bad things happened to him. The bottom of his foot is crushed. We found the boot. Actually, this is part of his femur down there, slammed into the boot. This is all we know about him. But when we look closely at these bones, in fact, we've taken them to a hospital here in Dallas to be CAT scanned. They tell us this is actually a part of the festered part of the wound that is now rock, that's preserved in the cowboy boot, which was made out of T-Rex skin. You think? It was actually made by the J. Letty Boot Company. And was made in the 50s. We have identified it from the stitch pattern. When the CAT scan came back, they had to have a name on it. It said, "Unfortunate Cowboy." We prefer to call him the Limestone Cowboy. One of my favorite fossils was from New Zealand. This is not a hat. This is a rock. Now, but obviously it doesn't take a long time. Some of you have seen the teddy bear that's petrified in the artifact room. When you look at the rapid and continuous nature of the fossil record, from the polystrate, that is through many layers, and the very detailed fossil, like the shrimp and the jellyfish and the ferns and the tall trees, you know these things don't happen slowly. You see the continuous and sequential layers clearly indicated by what's at the interface, the ripple marks, the little ephemeral bird tracks, and then Mount St. Helens demonstrating this very phenomenon. We see coal having to form rapidly, with the tree extending through two coal seams with many layers in between. All, by the way, we can make in 6 hours. Cave formations don't take a long time. Petrification doesn't. What is there about the geologic phenomenon that takes a long time? I love to talk about it. I want to talk about fossils and rocks in terms of the age of the earth. That's my briar patch. That's where I want to go. Love to talk about it. It's all rapid. Now then, why do you think the earth's old? It's not radiometric dating. That's not too good. It's certainly not the geologic phenomenon. That says the opposite. And all we've been talking about so far is the evidence for the old age of the earth, and it really turns out to be the opposite. Let's think for just a minute about some of the young earth evidence, which we haven't really dealt with, as described by anti-creationist W.D. Stanfield. Now, he hates the creationist, written several books of it, but he says, okay, there are some indicators of a young earth, which you haven't heard about, probably, in the textbooks. He refers to water from volcanoes and lava from volcanoes. And when we learn how much is coming out and how many volcanoes we have, there's some very interesting information there. We've got about 600 active volcanoes in the world today, about 10,000 inactive, which I think is primarily from the time of the flood. But 600 that are now active. If we take Paracotin, which is probably the most studied volcano in the world from down in Mexico, we know how it formed and how much gas is, and most of the gas coming out is the H and the O, the H2O forming water for the first time, juvenile water. Most of it is water coming out, and then, of course, the lava. But there's enough water coming out that would fill the oceans. 70 of the volcanoes like this would fill the oceans in a billion years. It's supposed to have been 4.5 billion. 600 of them would fill the ocean 8 times. And that's what we have active today, not counting the 10,000 inactive. What are you going to do with all the extra water? And, of course, nobody thinks all the water came from volcanoes. 4 of them, with the output of lava that we see at Paracotin, would account for the entire crust of the earth in a billion years. And, of course, a very small portion of the crust of the earth is from volcanoes. This says it's not that old, which Stanfield acknowledges. When you look at the pressure in oil reserves, we dig down and drill down and we tap some of these gas wells and it'll blow the rig way up into the sky. You've seen probably movies of that. How does this rock maintain the pressure as long as they say it's been there? You can measure the porosity of the rock, which you have to know in order to discover oil, know if the rock can hold the oil. And it's fairly simple calculation when you know the porosity to see how long the pressures could be maintained. There's no way these pressures could last more than just a few tens of thousands of years, but they're supposed to have been there for 4.5 billion or at least billions of years. We can measure very accurately the uranium accumulation in the ocean. Geiger counters, we can really, and we know how much is being delivered to the ocean each year and how much is there. Well, not just a minuscule fraction of what ought to be there if it's been going on very long. Same thing with radiocarbon in the atmosphere that we mentioned a moment ago. It would reach equilibrium in 30,000 years, according to Libby, who got the Nobel Prize for the radiocarbon system. It's not. It's about 20% short of equilibrium. Hasn't accumulated to that point and slows down as it approaches. According to Stanfield, the helium in the atmosphere ought to be at least 50,000 times greater than what it is. Now, since he wrote this, there have been some mechanisms proposed that could possibly explain that, but that's at least questionable. But that's his argument. He says there's the meteoric dust in the strata would likewise indicate a young Earth, and there are no meteorites in the strata. Some craters, maybe, obviously in some places on the surface. But here is this geologic column which records 500 million years of time. Where are the meteorites? It ought to collect them all the time, shouldn't it? But if it's a year-long series of catastrophes and just happen quickly, then we can understand there being very few. And we possibly have found a few, but there are virtually none. He says none. Population dynamics certainly argues for a young Earth. When you look at 2 people at the present population growth rate, from the time of the flood, time of the creation to the flood, you've got 6 billion people, at actually less than the present population growth rate. 2,500 years. What happens in 25,000 years? It fits our view, it does not fit their view. And these are the arguments of the anti-creationists. He says this is good evidence, and it is, in each instance. And there's quite a few of them. When you look at the evidence for the young Earth, there's a lot of good evidence, even according to the anti-creationist. When you look at the evidence for the old Earth, they're okay. Your radiometric dating and your geologic phenomena, that's not really very good evidence when you look at it carefully. We have more and better on one side of the scales. We have fewer and not so good evidence on the other side of the scales. Now, which is the better model? I think very obviously the best scientific conclusion is that the earth is young. That's what the scientific evidence, if you just go by the science without the philosophy and the religion, or just go by the science, it fits better. We have more and we have better evidence. It fits the facts best.